Okay, welcome to a video lecture supplement for Unit 5. And in this unit, we are talking about proving trigonometric identities. So we have a checklist for proving trig identities, and I wanted to work through some of the items as they appear on the test. And then we will look at some of the items in Pearson during the live stream published tomorrow. So currently, our test has several different trig identities that you are asked to verify. And so what I'm going to do is get some that are similar to the ones that you will see on your test, and we'll call that analytic trigonometry. It's right here, homeworks. Whoops. Come on. Pull this up real quick. And we'll work off of this document here. Okay. So let's begin by proving this. So here we have sine squared plus cosine squared divided by cosecant is equal to sine squared. And most of these problems on your test can be solved in 3 to 4 steps. I think there's one that's a little more than that. But most of these things are doable in a couple of steps, which is going to be a nice change from Pearson in that Pearson makes you walk through step by step, which is maybe a little bit harder than it has to be. So the big thing to note here about this test is that you want to always follow the checklist, which is step 1, we're going to check for Pythagorean identities, meaning we see squared trig ratios. Next, we want to check to see if there are simple ratios that we can look at our hexagon and figure out if they are product or quotient identities. For example, things like secant times cosine, which are just equal to 1. And then we also want to check during that step if we know any quotient identities, which again come off of the hexagon. And remember, that's as you move in a clockwise or counterclockwise motion around the outside of the hexagon. And then lastly, we want to check to see if the fact that we cannot do Pythagoras means that we need to write them in terms of sines and cosines. Basically, tangent becomes sine over cosine, cotangent becomes cosine over sine, secant becomes 1 over cosine, and cosecant becomes 1 over sine. And then we leave anything that's just a sine and cosine alone. And so, okay, so in this one, we notice that we have a bunch of sines and cosines, and we should recognize right away that there's a Pythagorean identity here. And then we check out of the 3 Pythagorean identities that we know that sine squared plus cosine squared is equal to 1, and therefore things like 1 minus cosine squared is equal to sine squared, and 1 minus sine squared is equal to cosine squared. But when we just have the exact trig identity here, we can take that out and replace it with 1. So sine squared plus cosine squared just reduces itself down to 1. And then every time we make a move that involves a trig identity, we want to write the category of identity that we're using out beside the problem once we take that step. So when I make a Pythagorean move, I'm going to write Pythag or some abbreviation that means Pythagoras out on the side of my problem. So next we can notice that secant and cosecant are defined in terms of sine by their reciprocal. So what that means is if you have a cosecant on bottom, it's the same thing as a sine on the top. So I can just write 1 over cosecant as sine of x. And the reason is this is reciprocal identity. And there we go. There's the end of the proof. This is the majority of what your test document is going to be like. Something that looks very scary up front, and then if you follow the checklist, it will very nicely reduce itself into the other side. And perhaps I should state that the goal with proving trig identities, or rather verifying trig identities, is that you want to take the more complicated side and then apply known trig identities and known algebra techniques to it until it looks like the right hand side. So I think that there are some folks in class who are getting hung up on, but wait, what do we do with the right hand side? And the answer is once you pick a side, you don't use the other side for anything except for to tell what the final answer has to look like. And you expect that your quote unquote final answer is the same exact thing as the right-hand side in this case. So just whatever side you pick, that's the only side you work with. So let's do another one, slightly more complicated. Okay, so we're going to work with this one. We have sine of x distributed through cotangent of x plus cosine of x tangent of x. And then that's supposed to equal to cosine plus sine squared. So cosine x plus sine squared. So again, we have to figure out now which side is the more complicated, and obviously the one with tons and tons of trig ratios. Let me move this up just a teeny weeny bit. Okay. The ones with the tons of trig ratios, that's obviously the side we want to work with. So please remember, once we do this, we're not going to touch the right-hand side at all. We basically just treat it like it's not even there, except as a reference point as to where to end. Okay, so recall, we're not going to touch the right-hand side at all. So let's go ahead and start doing things that we know how to do with the left-hand side. We always want to go in order. We want to check for Pythagorean identities first, and we don't see any here because there are no squareds on this side. There's no trig ratios squared, and there's no ones. So, okay, that's probably as good as it gets. So next what we can do is we can check to see if there are any product identities that we know. Now notice here that the um, cosine times tangent is actually a product identity. Cosine times tangent is on our hexagon, and so we notice that based on where the vertex for cosine and the vertex for tangent is, they're separated by the vertex for sine, and so that means that cosine times tangent will just end up being sine. Okay, so we've reduced that one, so we write everything else down. And then we write that this was what is called a product identity. Okay, so next we can say, all right, do we know anything about cotangent and sine added together? And what you'll find is most of the time when you have one trig ratio added to the other, unless it's something squared plus something else squared, it's not going to be anything. So that means that we don't know about this. But notice that if I were to distribute the sine through this parentheses, it would create sine squared x, which I'm supposed to have in my final output. And then we would have the product of sine of x times cotangent of x. All right, but we can again look at our hexagon for the product of sine and cotangent, and we see that those vertices are separated by the cosine vertex. So that means that this product is cosine of x plus sine squared of x, which is precisely the ending point that we were supposed to have. And what we did here was a product identity, yet again, and so we are done. Okay, so that one looked a little bit worse, but it turns out it's really not actually all that much worse in the long run. So then we have one that actually we haven't seen something like this before. We haven't seen it in Pearson, and we haven't seen it in any of the in-class lectures. We have 1 minus tangent of x all squared, all right, and then we have that equals to secant squared of x minus 2 tangent of x. So secant squared of x minus 2 tangent of x. Okay, so here here we need to be a little bit careful about how we pick which side we start with. So both of these actually look fairly complicated, but I'm going to say, frankly, that this looks more like some of the stuff that we've dealt with in the previous proofs, the in-class examples, the Pearson examples, than this side does. So I'm going to say this is probably the more complicated side, and remember, we like to start with the more complicated side. So just some algebra here. This says 1 minus tangent of x times 1 minus the tangent of x is equal to all of that stuff over on the right. But notice that this is a binomial term times a binomial term, and so we can FOIL this out like we would in college algebra. First, it'll give us 1, so then we'll have the product of 1 and the tangents. It's going to be minus 2 tangent of x, and then we'll have the product of tangents, which is plus tangent squared of x. And what you'll notice almost immediately here is that this term right here, minus 2 tangent of x, is something that we were supposed to get in our final output. So that means we're probably not going to do anything with this here. So notice how what we have is a 1 and a tangent squared. So if I reorganize these terms so that they look a little nicer, then you'll see that if I drop a parentheses around that 1 plus tangent squared, that happens to be a Pythagorean identity. And remember, every time I'm doing this, I'm looking for, do I see Pythagoras in here? And the answer is, yeah, I kind of see it. So I had to do some algebra to access that Pythagorean identity. So then we look at this one. Do we know any identities that contain a 2 and a tangent? And if you can search through the pink sheet and your hexagon and all of the class notes, you'll see that there's nothing there about 2 and tangent. So this is probably done. But this part right here, we have an identity for, and that is that tangent squared plus 1 is equal to secant squared. So that allows me to take the 1 plus tangent squared out to plug in secant squared, which is precisely what I'm supposed to get over on the left-hand side. So what we did in this step, again, we'd like to note it. I'll note it right here. We used a Pythagorean identity for it. And so we are done. Now remember, we're not documenting steps like algebra steps. So when I say FOIL this out, you're not going to have an instruction over on the right that says to do that. However, when you get into Pearson, my suggestion is all the drop-down boxes, do those parts of the problem first, because those are easier said than done. Obviously, the expansion of this binomial, when I tell you to FOIL it, you understand what that means, even if you're not entirely sure about what this is going to end up looking like when we actually do that operation. So saying what to do is actually a heck of a lot easier than actually doing it. As a result, click the drop-down boxes on Pearson, because that's like saying what to do, and most of you are actually capable of making the correct choice out of the ones in that drop-down. Then it's just a matter of figuring out how to use the thing that you picked to make it say what they want it to say. This one is really not all that bad. I actually really like that one. Okay, let's do a kind of complicated looking one. Some of these that I'm looking at are very, very easy, and so I don't want to do those examples because that would just be a worthless waste of time. But how about we do tangent of theta over 1 plus secant of theta plus 1 plus secant of theta over tangent of theta. And this is supposed to equal to 2 cosecant of theta. Okay, so on this one, our choices are extremely clear. There's nothing complicated about the right-hand side, so the side that we're going to pick must be the left-hand side. And the other thing that I notice that is happening is there are an awful lot of you who are getting hung up on the common denominator procedure. Now, the reason that we don't teach this in trig is because common denominators are a very, very fundamental skill, meaning we first learned about them in the 7th grade, and then that persisted through algebra, specifically your study of rational functions in the college algebra portions of your collegiate career as well as your like Algebra 2 portions of your high school career. So um, I'm going to show a way that a lot of math teachers will hate me for. But the point is, I want you to have a procedure that quickly computes the common denominator for trig ratios like this. So what we're going to do is we're going to pretend like any terms in a fraction that contain a plus or a minus. Okay. So tangent doesn't contain a plus or a minus, but 1 plus secant does. So we treat these terms inside of the fractions that contain pluses and minuses like they're in parentheses. Okay. So then what we do is we're going to take the top left times the bottom right, just like if we were going to cross multiply. It's just instead of cross multiplying across an equal symbol, we're cross multiplying across a plus or a minus. So we'll multiply those two together. We'll write down the result, tangent squared theta. Okay. Then we're going to steal the symbol out of the middle. If this is a plus, we steal a plus sign. If it's a minus, we steal a minus sign. And then we're going to multiply the bottom left times the top right. Okay, so the bottom left times top right, those are the same term. So I can write down 1 plus secant theta all squared over. Now the bottom portion of this is just going to be the product of the two denominators. So I'm going to write that as tangent theta times 1 plus secant of theta. And I know that a lot of you are going to be conditioned to attempt to distribute, and I would strongly caution you not to do that. Okay. In some of these cases, we need to make cancellations with things on the top and things on the bottom. And we can't very well do that if we distribute, because we may not be able to see the cancellations that need to be made. So I can immediately notice something. What I can notice is that 1 plus secant all squared is an example just like the last one that I did. So if I FOIL that out, remember that's like 1 plus secant times 1 plus secant, and you can see that clearly here. It's this binomial times this binomial. So we'll have tangent squared of theta, that's along for the ride, plus, foiling this out, we'll have 1, then we'll have plus 2 secant of theta plus secant squared of theta. All right, so now you have, I guess, a choice here. So first of all, I can notice that tangent squared plus 1 is the Pythagorean identity that's on our hexagon. Should probably write the denominator here. And so that allows me to change this entire tangent squared plus 1 into a secant squared. But notice that because I have secant squared plus secant squared together, that is 2 instances of secant squared. So I can replace this with 2 secant squared theta plus 2 secant theta all over tangent theta plus, times 1 plus secant theta. Okay. So now we need to look for some things that will make our life easier. Notice that there's no immediate cancellations because I've got a product on bottom. And this is a linear combination, meaning it's just like added or subtracted. I can't just go slashing out secants and things like that because they need to be identical. Basically, if I'm going to cancel something, look at the terms in the denominator. I must either cancel tangent out of the bottom and then each side of the top, or I must cancel 1 plus secant theta out of the bottom and each side of the top. Unless I can turn the top into a product, one thing times another. Now notice that that actually can be done. And what I'll do is I'll come over to this side a little bit. Make it a little bit easier to see. And then I will move this entire line of calculation up a little bit. So if I were to factor the common factor out of the numerator, notice that this is 2 secant squared and this is 2 secant. So both of those terms have a 2 and a secant in common. That allows me to write 2 secant theta times secant theta plus 1 over tangent theta times 1 plus secant theta. And now, since both the top and the bottom are products, this is one thing times another, and this is one thing times another. If anything is a common factor, I am allowed to cancel it out. So the secant theta plus 1 is common to the top and the bottom, so I can make that cancellation. Next, look, we have the secant over tangent here. So I could write that if I wanted to as 2 secant theta times cotangent of theta because of the reciprocal identities. And I should have noted here when I did this that I used a Pythagorean identity. I'm violating my own rules there. Okay. So we have 2 secant theta times cotangent of theta because remember 1 over tangent of theta is just cotangent, or in other words, if you have a tangent in the denominator, you can move it to the numerator and change it into a cotangent and vice versa. So then we can identify that secant times cotangent is on our hexagon. It is a product identity and it is just equal to cosecant of theta by the product identities. And that is precisely what we were supposed to end with on the right-hand side. Now, again, one thing that I need to stress in this video, because I feel like I'm going to just kind of rant for a second, and this is about the way that students think, and this isn't really about anybody in particular so much as it is you need to understand what is actually happening in this unit. And that's the hard part about this. What you are expecting from me is that I am going to come in and I'm going to teach you something that will result in an answer. And so if you do the thing that I have shown you, then you will get the answer. And this is a very serious problem with high school math education. What we are doing here is you are verifying that one side of an expression is identically equal to the other side of an expression. So to do that, you're being handicapped. A lot of the rules that you were told in algebra do not work here because to do a verification of an identity in the strongest possible way, we like to only manipulate one side of the equation or the other. So, takeaway number 1. I want you to focus only on the side that is more complicated and pretend like the other side doesn't exist unless you want to pretend like that is the answer that you're supposed to get. And you remember when you were given homeworks in the lower levels, if you are at my school, then they would give you the answer key so that you could do the process that they taught you and then check your own answer to make sure that it was correct. And I want you to treat it like it's that. Treat it like the more complicated side is the thing you are being asked to simplify. And this is your answer key. Okay. Thing number 2. The reason why this particular unit is considered to be so difficult is because you are building this from the ground up. You are suddenly responsible for knowing every single thing from the very first unit of trig, but also all of the fundamental skills algebra, from algebra 2 in high school, from algebra 1 in high school, from geometry in high school, and you're being expected to recall that immediately. And that's what makes this hard. You have to be able to go back to skills that you developed in algebra 1 and algebra 2 and even college algebra, sometimes even in geometry, to see how they apply to the problem. Third, what the identities do that you have on your pink sheet or on your hexagon, what you will notice is that they allow you to take a portion of the problem out and replace it with something that is more advantageous. So you need to get that inside your head almost immediately. Lastly, the thing that is also making this very, very difficult is the fact that you are being given problems that look insane. And frankly, they are. It's very, very crazy to go from the kinds of things that you were expected to do in college algebra and even the early parts of trig, and then suddenly have a problem that looks like this that has very, very few numbers in it. You don't need to be scared of the fact that there's no numbers. What you need to be looking for is patterns in the way that these proofs are done. For example, if you see a binomial containing a bunch of trig ratios and another trig ratio on the outside, that's like the second or third example that we did in this video. So what you need to do is go back on that part of the video, look at what I'm doing to solve it, and try that with your problem. You have to be willing to try that with your problem. And the biggest thing of all with this, you have to be willing to fail. If you fail, it means what you tried to do doesn't work. So go back and try something different. I also suggest, the reason that I've given out the test as early as I did, I suggest that you try a little bit with it. And then when you start to feel yourself getting frustrated, put it down. Don't sit there and force yourself to go through it over and over and over again. Put it down. Rest for a bit, and then come back and try something new. That is super, super important for learning how to do this successfully. Also, if you start to get frustrated with this, never underestimate the power of just staring at it for a bit. I know that that sounds like terrible advice. It sounds like the teacher who just gives you a problem and says, okay, do it, and then they never told you how to do it, and you're like, oh my God, what do I do? But with these things, you have the tools, you have the checklist, you know what you're supposed to try to do. Where the disconnect is happening in your mind is that you're not necessarily certain of what to try and in what order. And the only way that you build that kind of fluency is to see a bunch of these worked out and then to use the things that you have seen to try some of your own that look the same. In other words, if I change this to cotangent and that to cotangent, and I change this to cosecant and I change that to cosecant, and I change that to secant, how would you prove that? Well, look at the steps. Almost everything I did here, with the exception of which specific Pythagorean identity you're going to use and which specific product identity you're going to use, are the same. You know you're going to begin with a common denominator that will give you a term that has to be expanded. So binomial times binomial, like college algebra. You know that you shouldn't distribute the denominator. You know that that's going to result in a Pythagorean identity. You may have to factor something out of the Pythagorean identity there. Something will cancel, and then you'll have a quotient identity, which you can, of course, use reciprocals to turn it into a product identity to get the final side. Try to map the problems that I show you onto the problems that you have yourself. And that is the way that you learn how to do these. It's super important that you try. I hate to say this, it's super important that you fail. I'm not saying get a bad grade. I'm not concerned about that here. What I'm saying is it's important that you try things And it's important that some of those things that you try don't work. So what are you going to do? Put it down for 30 minutes and then come back to it and try a new thing. Persistence is the key with this.